Okay, support vector machine is a machine learning algorithm which is used for regression and classification, but mostly it is used for classification. So what does this algorithm do? It takes the jumbled data, it takes the mixed data or raw data and classifies the data into different classes, into classes of similar properties. Okay, we'll have a recap today. So here, how the classes are divided using a hyperplane. So here, what is the goal of SVM? The goal of SVM is to maximize the margin, right? This is the margin. It has to maximize the margin. So what is the optimal hyperplane? Optimal hyperplane is a plane or a region which is maximum, or the margin is maximum between the two different classes. Here you can see that the data points which are in red and blue, these are clearly separable. These are different data types and there is a clear separation between these data points. So this line is called a hyperplane. Okay, and so here what is the main goal is to maximize this hyperplane. And now, how to find the best plane? Here today we will derive a mathematical equation for the hyperplane. And here in this case, here the data is linearly separable, right? You can group the data into different classes easily by drawing a simple hyperplane. So here, what are these called? This red ball and blue ball, these are called support vectors. What are the support vectors? The points which are near to the margin are called support vectors, and the distance between this hyperplane and this green ball is called margin. And here also this is a distance between blue ball and the line is called margin. So what we do generally, we draw a plane which maximizes the margin between these two different classes or two different groups of classes. So what this is okay. Here the line is easy to draw draw between two different classes. But what if the data are jumbled? What if the data are jumbled? So how do we classify the data? So that is the main idea behind SVM. What does it do? It takes the raw data or jumbled data and divides the data into different groups by drawing a hyperplane. So here data, since there are two classes of data, and yes, if data is clear, we draw line. But what if the data is totally jumbled? We go for three-dimensional. That is, here it is, let us take, here data is clearly separable, right? Data is linearly separable. So how do we visualize? In order to visualize this separation, we go for 2D. But what if the data is totally jumbled? We go for three-dimensional data. That is, to have better visualization or to categorize the classes into different groups properly, SVM moves from two-dimensional to three-dimensional. Okay, here we are here in this case, hyperplane in two-dimensional is just a line, and in three-dimensional hyperplane becomes a plane, right? It's just a plane. So now here you can see this is a hyperplane. So here the data points will be mapped into higher dimensions until we get a proper segregation. Okay. And here the lifting of balls represents the mapping of data into a higher dimension. So that process is called kerneling. What is kerneling? Moving from two-dimensional to three-dimensional categorization. And we saw this equation, what if the data is not linearly separable? So what we do, we add one more axis, that is z-axis, and combine the data points x and y. We take the square. So basically z is coordinate, which is the square of distances of the points from origin. So now you add one more z. This is a z-axis. If you add one more z-axis, what is happening here? These points are lifted up, and now the graph becomes three-dimensional. So it becomes easy to categorize the data points into different classes. Now you can see if we shift from 2-dimensional to 3-dimensional, here you can group the data points into particular categories. And you saw accuracy pros, it gives, please remember, SVM works only for smaller data sets. Okay, and if the data set is smaller, it predicts well, accuracy will be good. And if the data sizes are more, if the data size is very large, then it performs poor on the prediction. And you saw different SVM use cases. It is used for text classification, such as category assignment, detecting spam, sentiment analysis. Can anybody tell what is sentiment analysis? What is sentiment analysis? Am I audible? Hello?
Yes, ma'am, you are audible.
Yeah, thank you. What is sentiment analysis? I'll give a hint. You're doing Amazon shopping, okay? And there you come across with different reviews of users for each product on the website. Why do they collect reviews? Yes, what is sentiment analysis? Have you studied this? It is a process of analyzing the user reviews, right? Whether if you give 4 out of 5, it is considered as a good review. If you give 3, it is neutral. If you give 2 out of 5, it is considered as negative review. So in order to study the user sentiments, or in order to study the user reviews about the product, so that they can improve the product quality in order to generate revenue for the system, they go for sentiment analysis. Sentimental analysis or sentiment analysis is basically used to study the people review or reports from the visualization. Okay, and SVM is commonly used for image recognition challenges. It performs well on aspect-based recognition and color-based classification, and it is also used for handwritten digital recognition, such as postal automation services. So today we will see the maths behind SVM. What you are studying here, what is hyperplane, how hyperplane is derived mathematically, and what if the data points are not linearly separable, how the hyperplane is denoted, and how to denote optimal hyperplane mathematically, and mathematical interpretation, and the SVM optimization. Okay. So this I think you already saw in the last class. Vectors, you know, vectors are the data points. Here what you see, OA is the vector. Here what is this? OA is the vector, and this shows the data points. Length between O and A is its. Here this is the length between O and A vector, and magnitude is A. A is the magnitude. So length of vectors, how it is calculated, you take different samples, x1, x2, x3. In this particular case, he is taking only x3 3 samples, and is finding the modulus of x, which gives the length of vector. And direction of vector is calculated as x1 divided by modulo of x, x2 divided by modulo of x, x3 divided by modulo of x. And here dot product of vectors, dot product between two vectors is a scalar quantity, and here you are taking the dot product and cos theta. Here angle between u and v, and u and v are denoted as x1 into x2 plus y1 into y2. What are x and y here? X are the independent variables, y are the dependent variables, or in other words, these are the outputs or the labels. And what is hyperplane? Mathematically, it is a plane, it is n-dimensional plane, or it is a plane that linearly divides the n-dimensional data points into two components. And it is also called n-dimensional line. And here you can say this data is linearly separable, and here it is not linearly separable. So you also saw that a hyperline, it's a line, right? Line is it is a point that divides two different classes. Y is equal to ax plus b. You already saw what is a, what is x, what is b, and x is equal to xy and y is equal to, sorry, w is equal to a comma minus 1. So how the hyperplane, generally hyperplane is denoted as w into x plus b. And what is optimal hyperplane here? Here what you can see from this diagram, since the data is clearly separable, or it is data is linearly separable, we can draw n number of hyperplanes. But what is our goal? In case of jumbled data, in case of complex data, our goal is to maximize the margin. See here, in case of this also, in case of linearly separatable data also, here our goal is to maximize the margin. So we have to go for optimal hyperplane. What is the optimal hyperplane? A plane or a line for which the margin is maximum. So here this is the maximum margin between these two classes, and here class 1 and class 2, and here we have to make sure that these three vectors, what are these three vectors? These three vectors are called support vectors, and there are two support vectors here. So our goal is to maximize this margin, so in order to enable the algorithm to make clear classification for the data points. And now let us see the mathematical interpretation of optimal hyperplane. What can you make out from this diagram? Here we have two different set of data points, and this is a support vector x1 and this is support vector x2, and distance between x1 and w and x2 and w. What do you understand by this? Yes? Here the line, this dotted line is above the hyperplane, right? This dotted line is above the hyperplane, so the y value is taken as +1, and this line is below the hyperplane, that is why y value is taken as -1. Now we have two variables, independent variable and dependent variable, for the data sets for the variables xi and yi, where I takes the value of 1 to L. It means there are L samples, L data samples, and how the output label is denoted. Output label takes the value of -1 or 1, where every x, for every x which takes the value of this R samples, and this D denotes the dimension. Okay, now if we take the value of D as 2, okay, if we take this value as D is equal to 2, here this is only, we will be able to plot the diagram using only x and y coordinates. Okay, and here we have two different classes. Class 1, these are class 1 points, and these two are class 2 points. Okay, now here H2 is the hyperplane which is above the line, and H1 is the hyperplane which is below the line. So now see how this distance between the hyperplane and H2 is denoted as D2, and distance between hyperplane and H1 is denoted as D1. So what is this minus B by W? Can anybody say what is this line? This line is orthogonal to the hyperplane. This line is orthogonal to the hyperplane, the point of origin.
Distance from origin.
Yes, it's okay, but what exactly it is? If you consider geometric margin or functional margin. Anybody?
Normal to the plane.
Okay, yes, okay, let us, for the time being, you can take that. It is a value which is normal to the hyperplane. In order to make this simple explanation, okay, this is the point normal to the hyperplane. And here, how the, this is the equation. And hyperplane, what is the equation for hyperplane? You already know. The equation for hyperplane is here there are two type hyperplanes, right? H1 and H2, and H1 is passing through the support vector x1 and H2 is passing through the support vector x2, right? So here x w dot x1 plus b greater than or equal to 1. So here hyperplane, if the line, if the dotted line is above the hyperplane, y value is taken as +1. If the line is below the hyperplane, y value is taken as -1. These two values represent the values of hyperplane. And here the two hyperplane H1, we have two hyperplanes, right? H1 and H2. H1 is passing through the support vector 1. Okay, H1 is passing through the support vector 1 and H2 is passing through the support vector -1 respectively. So if we combine these two equations, we get y is nothing but output level, okay, output level into w dot x1 plus b -1, which should be greater than or equal to 0. So this equation holds good for y is equal yi, that output level +1 or -1. So here hyperplane, how do you denote hyperplane mathematically? H1 is mathematically denoted as w into x plus b -1, and H2 is mathematically denoted as a w into x plus b is equal to w into x plus b is equal to 1. Okay. See here, I said the dotted line, this is the hyperplane, right? This is the main line. So here distance between this classifier and this is d1. So how h1 is denoted? H1 is denoted as wx plus b is equal to -1, because if the line is below this line, we take this as a negative value. So h2 is positive value. Wx plus b is equal to 1. So distance between hyperplane and origin, okay, distance between hyperplane h1 and origin, what is the distance here? -1, because it's a hyperplane is equal to -1, right? H1 is equal to -1. So the distance is -1 minus b divided by modulus of w, and distance between h2 and h2 hyperplane and origin is 1 minus b by w. You can go through this diagram. So this is the distance value. And how the margin, overall margin can be specified? M is equal to 1 minus b divided modulo of w minus, you take this, combine these values, you will get, if you simplify this, you will get m is equal to 2 divided by modulus of m. So see here, this m is equal to 2 divided by modulus of m. Why it is 2? Because we are taking combined margin, right? It is twice, this margin is twice, right? So that is why we are getting 2 divided by modulus of w. So in general, margin can be written as 1. It is twice the margin. So here in general, you can denote the margin as 1 by modulus of w. So this is the mathematical representation. Here, how our main aim is to maximize the margin. So 1 divided by modulus of w. So what exactly is w here? Yes, what is w? What is w? W is normal to the plane, right? No, W is normal to the plane. And this max of 1 by modulus of W can also be written as min of modulus of W. So this is the final equation. Ignore this. What is the final equation for the hyperplane? Min of modulus of W square divided by 2 such that yi W into xi plus b minus 1 should be greater than or equal to 0 for I is equal to L number of samples. And this is another graphical representation. Here we have negative classes. These are negative classes. It is taken as the negative samples and these are taken as positive samples, and this is the margin, and this is called, this is the hyperplane. So next. Now let us start the mathematical derivation. Hypothesis. What is hypothesis? Hypothesis with respect to machine learning model is the model itself, or which is nothing but our classifier, or it is basically a function. So this is the hypothesis function. H of the H subscript WB of X is equal to G into W superscript X plus B, and here Z value is equal to 1 if Z is greater than or equal to 0, or minus 1 otherwise. What do you understand by this? What do you understand by this hypothesis, general equation? Yes, students, I want response from your side. It need not be, communication need not be simplex. The communication or interaction should be duplex. Did you understand? Duplex, do you know what is simplex and duplex communication? Simplex means only one direction. Duplex, both direction. We would like to have interaction from you as well. When teachers are teaching classes, when teachers are conducting classes, there should be interaction between students and teachers. Then only you will get the benefit out of it. What is this G here? Okay, what is hypothesis in general? Yes.
It's like some statement.
Okay, statement which proves to be right or wrong? Correct? Okay, tell me, continue. A person is diagnosed as corona positive if he is actually negative. How do you define hypothesis for this? You might have studied this in mathematics, 3rd semester, 4th semester. It is a wild guess or a statement made on the basis of limited evidence as a starting point for further investigation. Okay. I'm not getting any definition. It's an assumption. Okay, basically is an assumption or an idea that is proposed for the sake of argument so that it can be tested to see if it might be true, to see if the classification is true, to see if the categorization or grouping is True. With respect to SVM, support vector machine, here whether we have to see whether the algorithm is able to categorize the classes into proper groups. So next is G value is nothing but it is input, and it depends on the input level and the normal to the plane, and this is what is B here? Ax plus b, y is equal to ax plus b. What is b?
y-intercept.
Sorry? Sorry,
The
yes. Your voice is breaking.
ma'am, the intercept.
Yeah, b is an intercept, right? X is slope, y is equal to ax plus b. Here, this y is equal to x plus b is a representation for line, and that equation holds when x is equal to 0, right? Y and b are variables on vertical and horizontal axis representing, and x is a slope and y is an intercept, right? So here y is equal to ax plus b is a linear equation in slope intercept form. Okay, now you can take that equation and input that into G. It is an argument. G of Z, it is a condition. H of X is equal to G of Z. Value is 1 if Z is greater than or equal to 0 or minus 1 otherwise. Next, class labels. What is class labels? Here we are naming the data points. Okay. What are class labels actually? We have to identify the data points from the raw data set. So class labels are denoted, or the input labels, what you can say, input labels or output labels. Here in this case we are discussing about output labels. So class labels are denoted as -1 for negative classes, +1 for positive classes in SVM. And the optimization problem for SVM, this is the final derivation. Now look at this derivation. Now we will derive this step by step. So this is the final derivation for optimal hyperplane. Min of half modulus of W square, stated that yi of W into x1 plus b, this condition, it should be greater than or equal to 1 for xi. Now here in order to derive this equation, you should have the knowledge of functional margin and geometric margin. What are functional margin and geometric margins? Have you studied in third semester?
No, ma'am.
Okay. Here, functional margin, it represents the correctness and confidence of the prediction. Okay. Functional margin, please note down. Functional margin, it represents the correctness and confidence of the prediction of the algorithm. What is correctness here? The functional margin should always be positive. Okay, the value of this functional margin should always be positive. And if W into X, okay, if W into X is negative, then Y value is -1. Otherwise, if it is positive, if W into X plus B is equal to positive, Y value is +1. Okay, so it is saying, it is giving us some number, right? Functional margin is giving us some number which denotes whether the plane is belongs to the positive samples or negative samples. Then what is geometric margin? geometric margin is the Euclidean distance between these data points, certain data points x to the hyperplane. Okay, it is the Euclidean distance between data sample x to the hyperplane, and this geometric model should be it is a scaled version. Okay, geometric margin is a scaled version of the functional margin. With this, we will move on to the derivation. So, a hyperplane is the notation for the hyperplane, which separates positive and negative examples, is denoted as phi, such that Wt, this Wt is W superscript T, Xi superscript T plus B is equal to 0. And here, yes, functional margin and geometric margin. Look at this equation, gamma of I. This is the geometric margin. Geometric margin is represented as gamma superscript I. So what is gamma here? It defines, this is geometric margin. So what it says is, it defines how far the influence of a single training sample example reaches for ith sample. Okay, I'll repeat, gamma, this gamma, it's a parameter. It shows the geometric margin. It defines how far the influence of a single training example I, simple training sample I reaches. Okay, if the value of gamma is low, okay, if we get the value of gamma is low, it means what? Look at this equation. You know, this is the equation for straight line, and this is the output level, and this is modulus of W.
Means the point is lying on the hyperplane.
Gamma, if the value of gamma is high or low?
When low, ma'am.
If the value is high, it means here we are dealing with I. It means we are dealing with every sample. Okay, here we are dealing with every sample. So if the value of gamma is high, what does it mean? Every data sample is close to the hyperplane. Okay, if value is low, if gamma I value is low, even the far away data point gets considerable height and we get more linear curve. Okay, if the gamma value is low, it means points are far away from the hyperplane and we get a linear curve. We get a more linear curve and the prediction will be efficient. The system, the algorithm will be able to correctly classify the data into categories or proper groups. So this is the equation for functional margin for each sample. Okay. So here, what do you observe? Here, this is the functional margin of a hyperplane with respect to ith sample. Okay, ith training sample. And how it is defined? Here we have a hat symbol. Okay, gamma hat superscript I, which is equal to y superscript I into the same hyperplane equation. So this is the functional margin with respect to ith sample. So how the functional margin looks like for the entire data set? Functional margin for the entire data set is defined as gamma hat is equal to min of all the data samples, gamma value of all the data samples, where I is equal to 1 to m. So this is the functional margin with respect to the entire data set. Next, geometric margin. Geometric margin with respect to ith sample is equal to y superscript I into hyperplane equation divided by modulus of W. So this is the equation for ith sample. and each hyperplane has a geometric margin with respect to the point closer to the hyperplane, which is the least of all other geometric margins defined with respect to all other points. What do you understand by this statement? When we take the combined value of geometric margin, yes, here it requires strong mathematical background. SVM, it involves a lot of mathematics. We have different points, class A and class B, okay? And hyperplane, each hyperplane has some distance with respect to the support vectors or the data points. And here every hyperplane has a geometric margin with respect to the point or a data point closest to it, which is the least of all other geometric margins defined with respect to all other points. It means here geometric margin of here gamma value of I, it gives the points which are at the minimal distance to the plane. And here there are some vectors. There are some vectors in class A and class B which are very close to the margin. And geometric margin for a hyperplane for the entire data set. So here we should minimum, here gamma value should be low, right? I said gamma value should be low in order to classify the data points into proper classes. So minimum value, gamma value should be minimum for all the samples for the entire data set. Next, here geometric margin should be maximized, and SVM algorithm maximizes this geometric margin by learning a suitable hyperplane or a decision boundary. So now here, if data is linearly separable, we can draw n number of hyperplanes. Here there can be any number of hyperplanes, but from the visualization we can see that this is the best hyperplane which is bifurcating the classes far away from this region, okay? And this is the red one is the hyperplane which has the maximum region, which has covered the wide region between the two classes, and this is the optimal hyperplane. So this can be mathematically written as WB max of the hyperplane value. So what is this? Look at this equation carefully. This is the derivation. How does SVM maximize the margin? By lowering the value of gamma, okay? Yes, what do you understand by this equation? Look at this equation carefully. What does this denote? W and B, W comma B, what does it denote? The objective function, it is here objective function, we are deriving the objective function of the SVM algorithm. Here objective function is the geometric margin of the hyperplane W comma B. And The objective function here, it is the minimum of the set of geometric margins of the hyperplane W and B with respect to all the training samples, okay, or it can also be denoted as hyperplane W comma B argmax. What is this argmax? What is it doing here? What can you observe here? Here, the geometric margin, it tells us that for the optimal hyperplane, the value of the smallest geometric margins with respect to all the sample values I is shared by at least one pair of positive values or positive class and one pair from the negative classes. So here we have vectors, support vectors. Positive vectors belonging to positive class, vectors belonging to negative class. I need not go more in detail. Try to understand from this equation. Hyperplane equation, this is normal to the plane. Yi superscript, it is output label. And you should minimize the value of gamma to predict the classification properly. Okay, any doubt so far? Here derivation, yes, it is self-explanatory. The equation is self-explanatory. Go through this equation carefully and try to analyze, and we'll see tomorrow. If you have any doubts, you can ask now. What does it indicate? Argmax, subscript WB. I already said this is the hyperplane, it denotes the hyperplane. Okay, we'll see tomorrow. If you have no doubts, we can wind off. Thank you. Bye.